Cool. We've got one more project, at least for the required sort of things, and then if you want to keep working, you can either go back and revise or work through Module 5. All right. Are we working through project today? Questions on that? Yeah.
So the last part of the project, we're talking about finding the minimum cross-sectional area.
Yeah.
Where it's less than, where the deflection is less than 0.2 millimeters.
Okay.
Is there a better way to do it than creating a for loop where you're iterating through? Is there a way to solve for a specific number, or is the way I started is using the for loop to say, plug in this value and it'll iterate through and it'll see what it spits out and make sure all the displacements are less than.
Yeah.
But that's imprecise because you're limited by your steps that you're taking in your ranges. Is there?
Yeah. So this is like same. Well, so there's two answers to this. One is recognizing, like we did in the homework. So let me pull up. Like when we were looking at that truss problem. All right, coming down. L not defined. All right. When we were looking at like the truss problem, and we said for a given force from 100 to 1100, there's some internal, and it's always linear, because if we're solving a linear algebra problem, the answer is always scalable by that amount. So in this case of like our linear algebra problem, we have, let's do a quick little F equals K X, where F is some vector of known applied forces, K is our stiffness matrix, X is all the displacements, or I guess we call it U, right? Usually that's the finite element way. But this is going to be E and A times, we'll call it like K star, where E and A are both scalar values, Young's modulus and area, and then times that same U vector. So if I multiply, if area is 10 times bigger, then U is 10 times smaller. So that's one way that we could do this, is that because we're solving a linear finite element problem, all our answers are directly scalable. The other way, so like option 1 for FEA post process. So option 1 is that bigger area is, the smaller deflections are. Option 2 is our like module 3 root finding methods, and whether we want to use like fsolve is like the SciPy version of those Newton-Raphson and bisection methods, or you want to go back and use like a modified secant or anything. But if we can set up, like define DISP FEA of A, like where our input is area, and then return max U minus 0.2, and this will have like stuff in it where we're solving the problem and figuring out, all right, what is that max displacement, subtract it from 0.2. When we find the root of DISP FEA, that would also give us an exact answer, well, pretty exact, like within floating point round off error. Yeah, so those are the two kind of processes. Any other things coming up, working through like project? Sometimes units are a little weird to think about. Again, question that nobody asked, but the K matrix that I give you is all in 1/millimeters. So if I want, so my consistent units are length are millimeters, force is Newton, stress and modulus. So any measure of like stress or modulus is a Newton per millimeter, like millimeter squared. Do you know what unit that is? Newton per millimeter squared? Megapascal. Yeah. So it's a Pascal, but over 10 to the negative 3, 10 to the negative 3, so megapascal. So if you're like, no, Professor Cooper, you're crazy, SI units are the way to go, millimeters just don't make sense, then make sure that you're converting that K matrix into 1/meters and not 1/millimeters. Otherwise, you'll end up with, I think it's usually off by 1,000 somewhere, either 1,000 too much or 1,000 too little, depending on what you're solving for. This is the units that I like to use in FEA in general, newtons and millimeters. So I'm not defining like, all right, this little part that I have that is 3 centimeters long is 0.03, and then I have to plug in like gigapascal is like 10 to the 9 values. Megapascal is nice. I know ANSYS likes to try to take care of the units for you, but you still gotta, in the background, the FEA doesn't care what units you're using. It can be all unitless if you want. And then what are the other things that comes up? So this extra FEA material, this has like some of the work that went into building that stiffness matrix. It also has like a little bit of post-processing stuff in there. But if you're looking for like why does the matrix look like this, this is kind of why. So we're taking, before in all the homework problems, it was all just springs stretching in 1 dimension. Now we have like springs stretching in 2 dimensions. It's kind of the difference between the first and the homeworks and then this one. So if we set up, coming down, like we can look at that same triangle problem that we were solving before, but now think of it as like, as we apply forces, it's actually stretching. So before we were just solving for some of the forces with 0, now we can actually use FEA and solve for where does it actually move to. And yeah, we can print out node array, conductivity array, all of that. And then let's see if this one works. Oh, it does work. Nice. you can, this is the problem that we're trying to solve in the project. It's just solved for one specific case rather than trying to like optimize anything. And there's a nice like slider thing here if you want to play around with like what does this thing look like as we go from really just scaling all the displacements by a factor, but it's the same thing as like increasing the force. It's like what happens when force increases. Cool. Let me check in, see where we're at. Or I could just randomly keep adding information in spots that may or may not help. That one is only plotting. Yeah, they have that. Oh, I don't know why. Yeah. This one is saying that like the whole, yeah, like the max value should be less than that. Because it's kind of like as the structure reflects, you don't want it dropping. So any individual value should be less than. Yeah. Yeah, I've seen people sum up all of this placement and try to close that. How do you measure that? How do you even know that it's true? You know, when you've done it. Yeah. Yeah. Yeah, I use the chart. Yeah. Mm-hmm. Yeah. Dynamics, but like dynamics, this one, I react first with this, and then talk about how you make it right. So we were having a nice conversation about like what the difference between this condition number and that condition number is, and why it's like 10 to the 16 difference, a factor of, or 10 to the 15. It goes from 50 to like 53 quadrillion or something. And the question was like, is this, when we do this one, is that boundary conditions? And it's like, well, yeah, that's the that's imposing the boundary conditions on it, but it looks like we're just taking a piece of the matrix and just calling that stiffness. So let's take a look. Like if we look at that triangle again, where this is node 1, node 2, or wait, no, I don't want to do that. I want to say this is node 2, this is node 3. And there's a reason, there's a method to the madness. So my first value is u1x, so left-right motion of that bottom left. Next one is u1y, up-down of that bottom left. u2x, u2y, u3x, u3y. And my stiffness matrix is going to describe how much force it takes to move any of those in any direction. So taking number 1 and like pushing it right up into the left straight towards 2 and 3 and keeping them the same, like there's a stiffness associated with that that's different than like taking all 3 and rotating them. Like that takes no force to rotate because we're not considering like momentum. So right now, if I just say like, this is my structure, let me apply an F here, an F there, and a 2F here. I mean, technically, I've satisfied sum of the forces equals 0, but my stiffness matrix is going to be singular. Like we end up with that same problem. Like I can solve this by compressing everything and keeping 1 and 3 in one spot and then bringing 2 down, or I could keep 2 in one spot and bring 1 and 3 up. Like I don't have anything constraining this thing. Rigid body motion has an infinite number of translations and rotations that would all, I guess not rotations, but an infinite number of translations that would still solve this problem. So I've got like some big K matrix. And in this case, I would be saying 0, F, 0, negative 2F, 0, F. So instead of trying to solve this first problem where I'm always applying forces everywhere, I'm just going to give it some fixed boundary conditions. So let's get rid of this. Let's say I don't know what that one is, and I don't know what this is, and I don't know. So I'm going to put in some forces that are just reaction forces, that if I know all the displacements, I could solve for them, but right now, I don't know what they are. And I'm going to say, so this one goes away, that goes away. So I'll put 1 on a fixed hinge and then 3 on a roller hinge. So that now these become 0 and 0. and this last one is also 0. So all these k values, like everything in these first 2 rows, I don't care what they are. And then same thing for this last row, because I'm gonna use these known displacements. I'm gonna use those afterwards to figure out what the reaction forces are. So the first 2 rows, the last row, and then those first 2 columns and last column is all stuff that I don't need to solve for. So by just grabbing that like middle part of K, now I'm plugging in boundary conditions that in those spots I have a known displacement that's already fixed. And that is kind of weird, but in more advanced FEA, like when you have like all these mixed boundary conditions, sometimes you have to like rearrange the stiffness matrix to kind of get everything into one spot. Here we've got a nice, like, only the first and last nodes have boundary conditions, but we can apply them anywhere we want. Yeah, so it is with boundary conditions, there's one solution. With no boundary conditions, there's infinite solutions. So condition number is very high. Yeah. Okay, nice. Well time. Yeah. Or distracting. No, definitely not distracting. Yeah, when you use that, I use salt. Yeah. That one is not salt. So it's right now. Yeah, so right now you have new salt for all three, or all the degrees. So every node of code node, you can figure out how far. But there's another quality displacement here with zero. Next in the line, should be 14 displacements. Yeah, because when you're solving object needs some stuff with those. So now I use a whole K, which is so K times a whole T times U solve for all 14. That one is U2. So U is a whole T side. U solve for that. Yeah, so the look at this here is yeah, with that side value, that one's going to give you a P element, but it'll still be, I think that one yeah, so this, when you have that lower matrix, first equation is 1 just U2x times 1 equals motivation. You only ever have one motivation. Then the second one, the opposite. And in practice, we need to do it. And of course, it does. That's the animation process. So you guys figure out not really, which is just figuring out how to read that key. Okay, so if you have the code that you solve, you just do it. Oh, the numbers that you figured out are just so you would look at that last P when you get log and log we add. Oh, at the beginning, you had two yeah, so now it should have 14. Oh, now it's like you're not even solving the problem, you're just saying k times 1 is that times. Mhm. You would just say k u1 and that'll print out all of this. A little bit. So, kind of setting up our linear algebra problem, we have like a scalar value of modulus, scalar value of area. Because they're all the same kind of elements, we can pull those out and now just multiply or divide by whatever those values need to be. And so here I'm splitting up into P, L, and U, and then solving. I guess one thing I didn't do was add that pivot matrix, but it's because I've seen it before, and it's the identity matrix, because this is a pretty like well behaved, and we don't have to worry about like dividing by 0 in our Gauss elimination process. But even if it wasn't, we could, in this solving step, I could say P dot transpose at that force, those applied forces. and first solve y is just like an intermediate step where I'm solving that forward substitution, and then u, this output u, little u, is the thing that I'm trying to solve for, all the unknown displacements. So I get, at least when I do this for steel, an area of 0.1. And again, I'm using like newtons and millimeters squared so that everything is like megapascal, newtons, and millimeters. And I get max displacement right here in node 4 y direction, 16 millimeters. So then the next part is actually even easier than trying to solve the matrix, where now I know every one of those displacements. I want to plug that in and solve for all of the applied forces. A lot of the applied forces I already plugged in, like that -300 and a whole bunch of zeros. Like most nodes have no external force applied, but there's node 1 and node 7 that have x and y kind of applied forces. So I'll call it like u total is not zerps, zeros, 14 zeros, and u total 2 through 13 is u, like the thing that I just solved for. So now when I look at what does u look like with the boundary conditions in there, there were 2 zeros to start, so node 1 in the x and y, 0 displacement, and node 7 had 0 y displacement, because it's always xy, xy. Now I can look at I can take EAK equals F, and EAK times U is F, and I want to use the @ symbol for the matrix multiply. And one of the things to double check, we get a whole bunch of like very small numbers, and again, this just goes back to like how well can we do math with this. Really, they would all be 10 to the -16, but it's a 14 by 14 matrix, so a little bit of floating point error adds up. Things to look for are 150 and 150. So at node 1 and node 7, we should have F over 2 because we're applying a force of F right in the middle down. And then, sure enough, a -300 right where we don't want it. Cool. Over the bell. But thanks a lot. See you again on Wednesday. Thanks.